We usually describe the weather based on how it makes our bodies feel, whether we need a heavy coat or find it too hot to work outside. But to understand the mechanics of the atmosphere, we must discard comfort as a metric. Weather is the real-time, highly dynamic thermodynamic state of the lowest layer of our atmosphere. A cyclone churning over the Indian Ocean is a massive heat engine in motion, governed by the laws of fluid mechanics as it converts thermal energy into destructive kinetic force. This real-time, localized variation of atmospheric variables, heat, pressure, moisture, is the weather. When we record these high-frequency shifts and aggregate them over decades to find stable patterns, that statistical baseline becomes the climate. For administrators and policy planners, tracking these localized, minute-by-minute thermodynamic anomalies is mandatory. A fraction of a degree shift in sea surface temperature, or a localized pressure drop, are the micro-triggers that initiate macro-level disasters, dictating everything from cyclogenesis to the failure of the annual monsoon. All of these complex fluid dynamics are contained within a remarkably thin boundary called the troposphere. This layer rests directly on the Earth's surface and extends outward to an altitude between 6 and 18 kilometers. The physical dimensions of the troposphere are not uniform. At the poles, dense cold air settles and contracts, compressing the layer to roughly 8 kilometers. Over the equator, intense solar heating causes the air to expand, pushing the boundary out to 18 kilometers. Within this specific, uneven envelope sits almost all of our planet's atmospheric moisture. It is the exclusive zone where cloud formation, precipitation, and active weather take place. The troposphere is a closed thermodynamic laboratory. The physical variables interacting within this 18-kilometer ceiling dictate the distribution of freshwater, the viability of agriculture, and where civilization can sustain itself. Every mechanism in this laboratory requires a catalyst to begin moving. That catalyst is temperature. The Earth is a sphere, which means solar radiation, or insolation, hits the equator directly, while striking the higher latitudes at a shallow angle. This uneven delivery of solar energy creates a massive thermal imbalance. Local geography dictates how that incoming heat is processed. A region's specific latitude, its altitude above sea level, and its proximity to the ocean determine how much thermal energy the landmass absorbs and retains. Because fluids change density based on heat, temperature differentials immediately produce atmospheric pressure differentials. When the surface is cold, the air above it contracts, becoming denser and heavier, exerting high pressure on the ground. When the surface is hot, air expands and rises, creating a zone of low pressure. The atmosphere constantly attempts to balance these pressure zones. Wind is the horizontal movement of air rushing from a high-pressure zone into a low-pressure void. If the Earth were stationary, wind would travel in straight lines. But because the planet is rotating, an inertial mechanism known as the Coriolis force deflects these air masses, to the right in the northern hemisphere and to the left in the southern hemisphere, twisting linear drafts into complex, circulating planetary wind systems. So the breeze we feel is the end result of a precise physical equation. It is the calculated output of thermal inequality attempting to balance out planetary pressure gradients. As this wind moves across the surface, it carries moisture. The amount of water vapor a volume of air can hold, its humidity, is strictly dictated by its current temperature. Hotter air can expand to carry vast quantities of vapor. Colder air can hold very little. When intense equatorial heat strikes the expanse of the Indian Ocean, it causes massive, continuous evaporation. The expanding hot air absorbs millions of tons of water vapor, generating heavy, highly saturated air masses. Driven by seasonal pressure shifts, these saturated wind vectors move inland toward the Indian subcontinent. Their trajectory eventually forces them into direct collision with the steep topographic barrier of the Western Ghats, where the heavy air is forced violently upward. This physical collision is called orographic lift. As the terrain forces the air to higher altitudes, the drop in pressure causes the air to expand and cool. Once the temperature drops to the dew point, the air can no longer hold its water vapor. It condenses and falls as heavy, localized rain. While this terrain-driven orographic precipitation sustains the Western Ghats, other regions rely on convectional rain, driven by intense surface heating, or cyclonic precipitation, where massive cold and warm pressure fronts collide to force condensation. The sequence is rigid and unbroken. Heat generates differences in atmospheric pressure. Pressure imbalances drive the wind. The wind transports humidity, and when that moisture is lifted and cooled, precipitation falls. Understanding the physics is only the first step. To transition from passive observation to predictive modeling, meteorologists have to convert this chaotic thermodynamic activity into standardized quantitative data. This image shows a standard data table tracking daily temperature fluctuations. By looking at the daily maximum and minimum columns over time, meteorologists can calculate the diurnal range and establish a mathematical baseline. Deviations from this baseline are the first indicators of a climatic shift. But relying on data collected only in populated cities leaves massive blind spots. Capturing dangerous anomalies before they strike requires pushing measurement infrastructure deep into high-risk geographic extremes. In 2023, the National Disaster Management Authority deployed automated weather stations, or AWS, at extreme altitudes, including glacial lakes in Sikkim, situated over 4,800 meters above sea level. High-altitude temperature spikes and localized pressure drops can rapidly destabilize these ice formations. The constant telemetry from these remote stations acts as an early warning bulwark, giving downstream populations time to evacuate before a glacial lake outburst flood can occur. Theoretical models show us how the atmosphere works, but empirical data tells us what it is about to do. Precise remote measurement networks are the bridge that turns climatology into actionable disaster management. When millions of these microvariable data points are collected, processed, and synthesized, they form the basis of our national alert networks. This official India Meteorological Department map visualizes thermodynamic anomalies across the subcontinent. Red states indicate a heat wave, a high-pressure dome trapping thermal energy. Conversely, thunderstorm alerts near Lakshadweep indicate steep pressure gradients forcing violent precipitation. The distinct colors and icons on this map trace directly back to the physical variables of temperature, pressure, and wind. These extreme events occur predictably when the tropospheric engine loses its baseline equilibrium. When the global baseline temperature rises, the total kinetic energy circulating within the troposphere increases. Adding more heat to this closed system guarantees that the mechanical outputs, wind speed, pressure differentials, and precipitation intensity will become increasingly violent and volatile. We are also introducing artificial variables into this equation. Dense concrete architecture and industrial emissions trap thermal radiation, creating intense, localized urban heat islands. These human-made thermal anomalies warp the surrounding pressure gradients, often triggering sudden, highly destructive urban cloudbursts right over our densely populated city centers. A thermodynamic anomaly does not remain an isolated meteorological event. A severe temperature spike alters rainfall patterns, resulting in regional crop failure. That agricultural deficit restricts supply chains, which triggers a national economic shock, forcing an immediate redeployment of administrative policy and disaster response funds. Every major climatic event, including the vast mechanism of the Indian monsoon, operates on these exact same physical rules. The planetary scale changes, but the variables, heat causing expansion, pressure driving wind, cooling forcing precipitation, remain constant. To manage a region's agriculture, infrastructure, and economy, you must look past the subjective experience of the daily weather. True administrative mastery requires understanding the invisible thermodynamic engine running continuously above our heads, because the physical limits of the troposphere ultimately